Hello and welcome to my video. This is the first video of my channel, and my channel is all about chatting and synthesis molecules, or probably some organic chemistry related stuffs, and I'll be gibberishing and speaking some stupid sentences a lot, so please forgive me about that, and just ignore me if I said something very weird. Yeah, so let's jump right into it. Let's first select the retrosynthesis. The first place we're going to cut is this bond on above this indole structure. So in the retrosynthesis we usually don't want to cut the indole structure because indoles are very cheap, commercially available and stable molecules and a stable core to be synthesized. So you usually don't want to cut in the indole, and as I just said, we're going to cut around the indole just like these three cuttings. So by order, the green is the last step to be synthesized because it's first to be cutted, and the yellow is the second one, and the blue one is the first place we're going to synthesize, which means that we're going to do reactions on the blue one very soon. Because this one just seems to be very active, it's the carbon 3 of the indole, which is nucleophilic, and the carbon 2 is electrophilic. So this specific directing effect of the indole making it a super useful starting material to be considered, because you can just put the groups to those places where you want. Yes, this is the Ambiguine P. Well, this big giant green plant is definitely not the Ambiguine P. So Ambiguine P is a naturally occurring indole, blah 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 blah, and yeah, it's just a random introduction I put over here. So it's produced by a cyanobacteria of the genus Fischerella, of this very long family, which I'm not going to read. I'm sorry. And this one, by some research, I guess this one is the Fischerella, the bunch st stonemata. I guess so. It's looking like this. They're very cute ones. And we're making this because that it's very useful in some drug discoveries. It might be useful, it might be effective to target some specific signals or something like that. Yeah. And whoa, what's that? I never thought animation was like, just put this bunch of lines around just like this. So I'm so sorry. Yeah. So just like this, we're going to use some might be seemingly new things to the reaction. The first one is the lithium hexamethyl disilazide. So this one is a strong base, as you can see, and the solvent is tetrahydrofuran, which is a really common one. It's a polar aprotic solvent and a very weird metal catalyzed stuff over here, which I'm going to introduce what is it used for. And let's first think about what would be happening. So obviously that if we're having the base, we're having a ketone with a very spare place to grab in hydrogen. Guess what happens? Yes, a very cool nucleophilic attack is going to happen on the alpha position of the ketone. And let's see what happens. And by the way, while we're using the THF here, is that this one could prevent the LIHMDS from aggregation, because as we can see, it can exist as a monomer or dimer, or even further, if you insert, just imagine that you can insert another mole of this one, another equivalent of this one, into this particular ring, making it a 6-member ring, 8-member ring, just whatever you want, so that this polar one could just prevent this aggregation from happening, making it more reactive, just as a heads up. Well, yeah, let's jump into the next reaction. So I'm going to apologize first. I promise you guys I wouldn't be doing this in the next video because this is just so devastating. I was trying to use the pen to draw all these mechanisms, however my Apple Pen actually lost in last weekend, which is pretty sad story, that I'll say. And yeah, so in the options left for me is using the Chem Draw and the handwriting styles. And very sadly I chose the handwriting style with my mouse. It didn't come out well. I'm sorry, but maybe you have to suffer it for a while. Yeah, for next video I'll probably be using some ChemDraw, some more fancier and cleaner style of writing all these mechanisms. That'll be good. So yes, just please forgive me about that. Yeah, so as we can see, the first step we're going to proceed here is the very typical hydrogen going off process. Yeah, we're going to have the base, which is the element HMDS, going to pull off this hydrogen adjacent to the ketone, which is a very typical reaction, and this one is going to attack, and this is the lithium is chelating nitrogen and oxygen, which kind of guards why it doesn't extract the hydrogen over the opposite side. You can think of the resonance. It is indeed acidic, just not so acidic, just like this alpha hydrogen. So the gamma hydrogen is also very active, but since the chelation might be more favoured of this alpha hydrogen. For the next step, so this is when the copper kicking in. So the copper with a bunch of ligands, as those are not very necessary, I guess, just a random ligand. And this copper is actually used as a directing effect, a directing things. Yeah. So what it does is that it's just like a Lewis acid, but not necessarily like a Lewis acid. The nitrogen is trying to have a little bond with it, and then the carbon-3, which is originally a nucleophilic site, will soon be electrodeficient because the resonance will kind of push it to resonance electrons to the nitrogen, and this process will be more favoured. Then we'll attack on the carbon-3 sites, then pull off and do a simple workup by the base. When I write B, it means base, and pull off a hydrogen, which the base will usually be the lithium HMDS. I mean, in this reaction, and then do a simple workup. You got this very big, nice molecules and form the CC bond between the indole and this ketone. For the next step, it's a alkyne with a LiHMDS again. It's just like the conditions before. It's a THF and with -78 degree, and this degree is actually very critical because if you are doing this reaction in very high temperatures, it's very dangerous because the LiHMDS is very active. If you have ever heard of the LDA, it's a very common things as well. Usually do those reactions in some low temperatures to make it more, first of all, make it more kinetically controlled. Second of all, it's just more safe. It's safer, and you don't want your reaction bowl to be like exploding. Yeah, so that's why. And the mechanism follows by this. Still the base, extracting the hydrogen and the terminal carbon of the alkyne. Now the terminal alkyne is actually quite a stable one, the anion of the alkyne. That's because the orbital is sp hybrid. It's sp compared to those sp3 orbitals. The sp is relatively more stable because the s is taking more proportion in the orbital, making it smaller. You can consider the shapes of the orbitals. The p one is a lobe and it's really long and big. For the s is just like a sphere, and it's like a sphere and really small. So just think about that. It's just less diffused, which making it more stable to exist and easier to be pulled off. The hydrogen is more acidic if you look up the pKa's. And then just proceed a really easy attack. Preceded by a very easy attack. This Lempere is going to attack the ketone nucleophilic addition, and then for the next step, we're looking at the PDC. I'm sorry, I didn't put the names over here. You can go up, search that for yourself. It should be very common if you're doing organic chemistry because this is a very common oxidizing agent, and it's very useful, but it's a bit too toxic, so I guess you can't avoid that. You can't put chromium in the reactants, so yeah, it's pretty toxic. And this step is the first step where it might be a bit tricky, because that when I first saw this reaction, I thought this OH is going to attack this specific double bond, and this one kick back and knocks off. Then we're going to oxidize it, but actually it is not the exact procedure. It takes the mechanism is not like this, and actually it's a named reaction. It's called black adsorbent oxidation. So first, the oxygen itself wouldn't directly attack this double bond. It might be some energy barrier issues, but it'll attack this PDC. You see the PDC actually got this little gremlins inside, and then we're going to attack from there. Sorry, that was a hydroxy group, not a chloride, but you can take this as an example, because I took this picture from somewhere else. I don't want to use my handwriting to kind of mess up this entire thing. I'm so sorry. And by using the picture, you can easily see what's happening over the places. So basically, it's that this gremlin oxygen is just like this original oxygen is on this new carbon of this place. I'm sorry if you can see my cursors around. I'm going to swing it. It's a bit more stronger, and then take off this hydrogen, knocks it off, going back. So at the step 2, it's just like the oxidation mechanism of the PDC alone, but the first step is quite tricky, and if you figure that out, great, that you're a genius, I can promise you. And then we're going to form this very good alpha beta unsaturated ketone afterwards, and by some after work up by some acids, we're going to clean up those PDC residues. Reacted over residues. That'll be better. And yeah, let's see. The next reaction is quite a monster. This is like a Godzilla of the chemistry I first saw it. It's really terrifying. It did terrify me. So this reaction is a named reaction called Nitriles reaction, but don't be kind of misled by this conditions. The boron trifluoride is not necessarily conditions for the Nitriles reaction. It actually leads to another very important intermediate of this reaction, which you can probably guess. And this is the CO2-COA to the cobalt CO complex of this. It has 2 states of it, and then okay, we're looking at the mechanism of the Nitriles reaction. So the first step of this entire reaction is just to add this complex to the triple bond that showed over here. And note that it must be a triple bond. If a double bond, that doesn't work. So it must be a triple bond, and this is CC triple bond, which makes it to form a cute complex with this CO2-COA. But this mechanism haven't been studied yet. I did a little bit of research, but I haven't found any papers that just directly indicate the process of the mechanism of this process. So just might be thinking that there's a pretty weird way of doing this. So yeah, that's pretty cute. And then a loose acid is kicking in. The loose acid is catalyzing 2 steps actually. The loose acid is first trying to catalyze this OR group to go off. So this O is kind of attached to the BF3, then goes off. And as well, and another thing to notice that the CO on the cobalt is going to utilize this loose acid as well, because if you think about the orbitals, it's a CO and CO3. This particular complex is actually super stable, because you have the pi back effect, say sigma donor and the pi acceptor of the CO ligand. So this one is going to be super stable. You have to use something to make it reactive. So what we use here is loose acid. This loose acid will interact with this CO on the cobalt, and then making this the cobalt. I'm sorry, I'm using a bunch of COs. It's too hard to distinguish. I'll just say cobalt. The CO will kind of interact with this loose acid and making the cobalt a bit more cationic, just make it slightly more stable, and the nucleophile can kicking in, trying to attack this position to make the energy level lower, and then followed by an oxidation, finish up the cleaning of this complex, and it's done. So what does that? So what it is that if you have an OR group that's adjacent to CC triple bond, you can use this conditions to make this OR, this particularly OR group, very 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 good leaving group. That's what it does. Well, I mean, if you just looking at the reaction step per se, it's just turning the really good leaving group, but in fact it's not. It's a very complex reaction mechanism, I guess. Might be a bit complicated when you're first doing it. So another question actually kicks in, is that why we are doing the nucleophile attack, the nucleophilic attack over this carbon 2 positions. So why here? Well, this is actually because that why we're having this concerning is that usually we're having the a nucleophilic attack on the carbon 3, because this nitrogen can have a resonance. This lone pair could have attacked this carbon 2 and then bounce off the double bond to the carbon 3, and the carbon 3 can act as a nucleophile to attack the other things. But why we are doing this over here, other than the carbon 3, as I just said? Well, actually, it is indeed originally here. The carbon 3 indeed acts as a nucleophile. However, there's a really cute rearrangement that's catalyzed by the loose acid of BF3OET2, which is the boron, trifluoride, and diethyl ether. Yeah, and you might be thinking that why are we having the OET2 present at this point? Well, that's because of the BF3 per se is a gas under room temperature. As you can see, it's just very directly noticed that it's room temperature of this reaction. So we must be having, we have to form some sort of complex to make this gas essentially a liquid. Well, over here we just use OET2 to do so, and it's a really common way to make it just a bit more stable, to make it in the liquid so that it can react with other things. And this is the mechanism. This is from the Organic Chemistry by J. Clayton, the really classic and famous book. Well, I do this, I'm so sorry, I just used someone else's pictures again. I think I'm going to do that a lot because I haven't registered my Chemtrail yet. I'm going to do that really soon. Again, I'm apologizing for it. Sorry, Clayton, I'm using your pictures. Please forgive me. And this is going to be pretty cute reactions again, because this rearrangement is just fabulous. You can see the mechanism over here. Just attack. Just nothing to say about it. This cation is sitting on this side, and this is a tertiary cation, and make the energy barriers slightly lower. That's what it does. So yeah, really fancy step. And note that this particular cobalt complex is still sitting on the triple bond because we haven't got any oxidation steps going on yet. This is a common solvent that's non-polar. Well, wait, I guess it is a polar. Well, wait, am I tripping? Yeah, this is non-polar. Yeah, it's CH2, so it's CH2Cl2, so it is indeed polar and aprotic as well. The next step, this is the Friedel-Crafts circulations. As I just said, it's on the benzene ring, and the directing effect you can see is from the nitrogen. Very easy, just attack this side, this side, making this positions slightly more nucleophilic compared to the others. I'm sorry, wait, where's my cursor? Oh, it's over here. I'm so sorry. You can thinking about that. The positioning of this giant molecule. It's quite fascinating to see, indeed. And this is a very typical Friedel-Crafts circulation conditions by using the aluminum trichloride. And then to proceed, I'll show the mechanism. Still, my bad handwritings by mouse. This is the hardest work I've done. Yeah, just using the mouse to draw up those delicate little mechanisms. It's super ugly. I can't even watch it. So the double bond will first act as a nucleophile to attack the aluminum. This is a slightly more positive side on the tertiary sides, and then the benzene is going to do an SEAR reactions on these positions. And then the hydrogen is going to be pulled off and retraced back to on the carbon again to make this benzene again. This is an aromatic ring, so we can't lose the aromaticity. have to draw off that hydrogen and pull this back and reform a double bond again. Am I gibbering? The next step is quite impressive actually. The ET2 aluminum CN. This is a brand new reagent that I see, because I've never seen it before. I don't even know it has a name, but after some little research, it does have a name. Sorry, this is called Njardarson reagent. This one essentially just a source of the C and anion. It's a source of that, making it super reactive. And here we got the pyridines aside and the TMS Cl, the trimethylsilyl chloride, and the pyridine aside. I'll show the mechanism. So this pyridine is essentially a kind of a Lewis base sort of things. It's donating electron to the aluminum, making this CN more probable to go off. Yeah, I'm so sorry. This bond should be linking to the carbon other than the nitrogens. Yeah, that's a huge mistake and make the reaction completely different. But anyways, just like this bond will go off and kicks the 1,4 position of this one. Actually, it's quite, actually I'll say the orbital is quite big, because the anion lies on the carbon. And the carbon has a low electron activity, making an orbital, making it like entirely orbital extremely big. The electric cloud is extremely big, so it's very soft, and soft will usually attack the 4 position will do 1,4 additions. This is what happens here. And this structure is just TMSCl. It's a very common things for protection. You'll see a while later. And this one just started to attack this Si and knocks off the Cl and Si bond. Don't really have a big bond energy, so it's very easily to leave for this chloride. This is what happens. And then next step is going to be the reducing agent overall, because that we're going to deprotect, because that we're going to reduce this big little complex over here. It's very essential to protect this ketone group, otherwise it'll be reduced, and that would be just complete disaster. Well, be not disaster, but you have to like do that again, so why not just infuse it with the last step? And that is actually pretty quick to do so, and very easy. So what we're doing here is that we're using a very it's a free radical reducing agent. Just keep that in mind, that whenever you see the Bu3SNH, this reagent is going to be a free radical reaction. I hate to see it. Free radical reactions are just so hard to handle around, and it's hard to draw the mechanism as well. So many side products. This one is actually slightly more selective. Anyways, after the reducing of this big metal complex, which I'm not going to draw the mechanism because it's too complicated, next step would be to, here we got then 2 moles of 2 equivalents. There, 2 moles of HCl is added. The HCl is a good way to deprotect the TMS group. There is other ways to deprotect the TMS group, but they used it here. It's a very clever way and very quick way, not very harsh. Just use it. Then the deprotection will lead to a quick regain of this ketone. This is the mechanism. So the O is going to get in touch with one of the hydrogens, floating hydrogen cations, and then H2O is going to tack back, and then just a enol transition. Going to get far more ketones than the enol form. I'm sorry, my throat is yeah, sorry. Next step is a hard one, yeah, because this is a reaction that's cited in those synthesis paper, which means that the mechanism might just not be presenting on the internet. You have to figure it yourself, and some of them don't even bother to find out in the mechanism because they just did it like it's in a paper. I can provide you some like simple mechanism, but however you've got the metal complex here, so it's not going to be simple. Yeah, and it's in the paper. Actually, the metal mechanism is indeed included in the paper, which I'm going to link down below in the description. If you're interested in it, just feel free to check it out. It's very useful, and it's a fun way to learn chemistry. But I'm going to warn you, that's pretty hard. It's pretty weird as well, and we're going to use this weird reagent. Here's the Aldoxime, acetodoxime. Yeah, I guess that was the pronunciation. If I'm wrong, please tell me if I'm wrong. I'm not so confident with these pronunciations anyways. We actually got two different products in the way. One of them is this one. One of them is this one. Could you please spot the... could you spot the difference between these two? It's just that the nitrogen for this minor product is not attacking this specific ketone group. But for this one, the nitrogen did attack the ketone. So that's the difference. And the ratio is approximately 1 to 2.3. Now this is the reaction I was saying. You can presumably think in the reaction mechanism as this OH group is going to attack this carbon of the CN of this nitrile group. This OH is going to attack this nitrile group, and this N group is like worth some little interactions with the metals, making it super active and very easy to leave, and then do it again. The procedure, this is going to attack this carbon again, knocks off this nitrogen, is going to chelate it with one of the ligands or just metal itself. You can think of it that way. You can get a little bit of feeling of what's exactly going on. But if you want some detailed explanations, please just go check the papers. I'm sorry, due to copyright problems, I don't think I can present it here. Yeah. For next step, we are using some methyl formate and the Na version of the HMDS. Now, this is a problem worth considering, is that which one is more reactive, do you think? The Na HMDS or the Li HMDS? Now, I'll give 3 seconds to think. Yeah, obviously Li is more reactive because Li has a low electronegativity, and also if you are clever, you can actually spot the difference between the reaction conditions. It's in room temperature, means it's less reactive, it's just less volatile, less reactive, but not necessarily less volatile, but you get what I mean. It's less aggressive, quoted aggressive. Yeah, still using a THF, just keep that in mind. Oh, this reaction mechanism is a bit harsh that I drawed over here. I kind of skipped some of the steps, so this is not a standard and the correct way of drawing mechanisms, so sorry about that. So very firstly, this base will kind of extract this hydrogen from the hydroxy group. It's going to attack, bounce off this nitrogen group, and this nitrogen will attack the methyl formate, and then just by acidifications on this OH group, this hydroxy group. Well, this is not in one step. This actually should be divided into 2 steps. One of them is acidifications, and the next step is the knocking off of this water. The next step as well is by drawing off. It's just a kind of aldo reaction type of things. It's by knocking off the hydrogens on alpha side of a ketone and attack another equivalent of this. What am I saying? It's not another equivalent, just attack this Me group. Should be fairly easy to see, or it might be not because it's my mouse writing. It's very bad. It's really bad. It's very bad. And next step is very common, NaBH4. Well, if you don't know about this one, just make sure that you checked your course book. Well, this one should be the first reagents that are presented as the organic reducing agents in your A-level course. Or if you're not studying A-level, I'm so sorry. I'm being a bit sarcastic, sorry. This is a cute reduction. This is usually the reaction mechanism present. However, there's some more side reaction, which means that one equivalent of NHPS4 can actually reduce up to 4 ketones. That's another topic we're going to discuss another day. There is some magical things happen at the backstage of this reaction. Next test we're going to... Oh, I think I just forgot to type the name of this reaction. It's trifluorosulfonic. Trifluorosulfonic. It should be right. Trifluorosulfonic. This TF, which is standard for that. Oh, there's a di. Sorry, the di as a prefix. Sorry, because there's 2 of them. This one plus this big random things which you don't even have to bother. This big long 2,6 ditert butyl pyridines. What does this do? I don't even know. It's just random things. So this one essentially just makes this big things bounce off. Reaction mechanism should be looking like this. Or this one is actually been noted in the paper because the mechanism is unknown. This one is the predicted and hypothetically the right mechanism. So nitrogen is going to attack to the ketone, and ketone is going to attack the TF2O. It's going to be protected as a OTF. Oh, it's not protected. The OTF, a really good a leaving group, is going to be knocked off once again by a the OMe group is going to do this kind of cascade on this molecule, forming this structure back. I think it's quite impressive actually. Next step should be using the TCDI. Usually you could see some CDIs in those papers, but nowadays usually use TCDI a bit more. It's easier to synthesis, I guess, presumably. DMAP as a catalyst. This DMAP is a really common catalyst for nucleophilic attack, and also it could appear in those competitions for high schools. For example, for the 2023, that's 2 years ago, they ask you to, in a Canadian chemistry Olympiad, they ask you to draw an exact mechanism of this, the DMAP catalyzations to the catalysis to one of the nucleophilic additions. I'm sorry, nucleophilic substitutions. Yeah, it's quite cool. Just by looking at the exact mechanism. So this one actually came a bit weird. This nitrogen at the above would actually take some advantage by donating its electron pair to the aromatic system of this pyridine. I'm sorry, I can't speak right now. My throat is soaring. And then I'm not going to talk about this one. Just look about your eyes. Yeah, this is what happens. So at the last step, this DMAP actually regain its aromaticity by some cute steps by knocking off it and leaving. So essentially what it does, that it actually acts as a good leaving group and also a good nucleophile, just like iodines. If you know about the Finkelstein reaction, the Finkelstein reaction is basically you put iodine, which is a really good nucleophile, and it's also a really good leaving group. So by using that feature of it, you can do by first using it to knock off the bad leaving group, and then itself act as a good leaving group, making your wanted nucleophile to attack this molecule, to attack this electrophile more easily, because the DMAP is now the new leaving group and it's very easily to be knocked off. It's a very good leaving group now. Since you can regain your aromaticity back, it would be a good leaving group. It's energy, so energy-wise, it's more favoured. Next step is going to be. Wait a minute. Oh, I think I misplaced the reaction. Actually, for real. Oh, you're joking. The next step should be the Barton-McCombie deoxygenation. Well, I think I just accidentally. I'm so sorry. So let's first look at this one. So the OH groups is turning to this giant big group over this place, and what it does for the next step is that it uses the Barton-McCombie deoxygenation to essentially erase this big group. So what it does is that if you compare the starting material, it has a hydroxy group, and this hydroxy group after this set of reactions, and by adding those Bu3SNH and a bunch of them sort of stuffs, what you could get is that you completely erased this oxygen, just like this. So you originally have a big group like this, and you just erased it. That's very, very interesting. Just ignore the SME and that CDI over there. It's basically the same thing, just by another way of doing so. It's not necessary to make it SME. It could be just like this TCDI one. It could be another things. The imidazole. Yeah. So for this reaction, what you get is that the TMS CH2, I think it's in the next page. Yeah. This is the next reaction that I misput on the last page. Actually, you can see that you've got the TMS CH2Li, which acts as a nucleophile. It's trying to attack this ketone side, and just mark that. Here we got a microwave, which I'm going to tell you what is it about, and it's going to attack the aldehyde and go into this aldehyde's oxygen by cascading. Just attack this CM group, form a weird structure like this, a lactone-like thing, and by some workup, you just get that. And what it does is that. So basically, the microwave is a good way of heating up the things. So if you look at the THF, the solvent, and the temperature we used over here, it's 120 Celsius degree, which is impossible for the THF because THF only has a boiling point of approximately 60, 70, that sort of degree. So that's impossible to heat it up to 120 if you are using it in a kind of opened containers. So you have to put in a vial and then do microwave to heat it non-conventionally to make those THF essentially into some gas sort of state and make the reaction extremely fast, because you're not doing this by conventional heating but by microwave heating. Everything is just like a gas bumping everywhere, making the reaction so much faster. If you're using conventional heating, could take hours, probably days, but if you're using the microwave, it only takes a few minutes, and it gives the molecules more energy to overcome the activation energy and could be forming a higher yield, I guess. These are those things you might want to consider. Some very cute ones, very cute reagents. Yeah, so this is what it does. The PBDS and DC, just looking up things. This is the exact mechanism. Yeah, the PPDS is trying to act as a. I guess it's trying to calculate about that, just to do a little bit of interactions with oxygen. I don't know if this is right. I'm sorry. And for next step, having T-bath and THF. Now T-bath is a very common fluoride source. Now what does fluoride do? This is what I talked before, that we've got various ways to get rid of TMS. This is the other way, by using a fluoride group to get rid of the TMS. However, this is another completely other mechanism of doing so, because this TMS is attached to a carbon, but the last TMS is attaching to oxygen, and oxygen could have took another acid, but for this one you can't really do that. You can only use the fluoride to knock it off, because carbon couldn't take any protons floating around, so This is a kind of aggressive way of doing so. This shows how the TMS can be deprotected in various ways. It's very fascinating to see how this one group can react with so many other groups. Just my own opinion. And this is a cascade type of reaction as well. Oh my god. This fluoride is having a really good bonding to the Si. That's probably due to the very big electronegativity difference between the Si and fluorine, because that they are very polar. This bond is very polar because the electronegativity difference would be up to 2 between these two, which makes the bond energy extremely high. The bond is very strong, and it's polar. So it's obviously stronger than the covalent bond, and the orbital overlapping is also quite good, even though it's 3p to 2p, but the F is holding its it's holding its electrons really tightly, making the orbitals really dense. I like to say that word. Just overlaps really good to get it really dense for the fluorine. Yeah, and the bond length is also very short because fluorine's short. Fluorine is a small one. If it's short, the bond energy should be high. That's the rule. Yeah, so based on these factors, it's a very strong bond. So F has a very big affinity with silicons, and just like the O and just like oxygen and phosphorus have a really high affinity, so it can act as a nucleophile to attack the silicon, and then due to a cascade, this reaction will look like this. Looks like this. Yeah, the microwave, as I said, yeah, it's indeed at 66 degree, just like this. Okay. Oh, animation, cool animation, got to say. Now this step is going to be a Hofmann rearrangement reaction for the beta and KOH used. K is a very strong base, just like Na, just like sodium hydroxide. Potassium hydroxide is also a very strong base used over here, and this beta is essentially acting as a bromine, because this is a Hofmann rearrangement. Let's see the mechanism. Now this is from Wikipedia again, just like the Nitriles reaction. I took it from Wikipedia because I've checked by myself. I think this is a fair mechanism. Yeah, just like this. This is what happens. You can check it yourself. Okay. And next step, using the acetic anhydride. This is acetic anhydride. I forgot to type the name. I think I go with search AC2O, common one. This is HCO2H. The methanoic acid is going to attack this acetic anhydride and knocks it off, and then NH2 is going to attack this big bunch of this reaction. Yeah, this one is just essentially part of these two reactants, and then the nitrogen will attack this acid site, making it just like this. So aldehyde is produced. Nothing too special. The next step is quite a tricky reaction, that I say, because I can't really draw the mechanism very well. So what I do in the second step is that I think it is sort of like a cyclic structure, because otherwise you can't say it's an isonitrile, making it the carbon should be bearing a negative sign on it. So I have to find a way to sort out where does the lone pair come from. So what I've conceived of is that this particular nitrogen is going to attack at this carbon first, and this oxygen is going to attack this ketone again, and then this will leave as a carbon dioxide as gas, and this chloride will be bounced off, well, obviously, and then it will pull off the hydrogen from the alkyne, not necessarily alkyne, the isonitrile, because it's quite acidic. Yeah, so I guess this is what happens. or probably the nitrogen will sort. The oxygen will replace the role of the chloride, but I don't think that's quite possible, because you're going to leave with a not a CO2 but another type of molecule. So I don't know what is it. I don't know the name of it, but it just sounds really weird. I think this makes sense, because say CO2 is knocked off, energy should be fine. I guess this was the mechanism that provided. If you have any new thoughts on this mechanism, please tell me. Please just message me, whatever. Just please, yeah, comment down below. Yeah, I really need that. Yeah, next step is a elimination. I didn't add any animations over here. I didn't add any animations. So this one is quite a. I don't know if I drew this mechanism right, but I think it would be indeed just like this, because otherwise the C and isonitrile couldn't. I don't think it can easily just leave like this, because you're left a negative sign on it, which is quite not favoured in my opinion. So I think this DMSO, even if it's a sort of solvent, of course it's solvent, but as well, I think it can act as a loose acid type of thing, because SOs can be divided just like this. It can be, the bond between S and O can be broken just like this, or it's at least it's partially positive and the nitrogen is partially negative. I guess it makes the carbon sort of form some interactions with the sulfur, and thus it's easier to be knocked off by this TBU this TBU group. CBO group is a really good base, you can imagine, because there's a whole bunch of carbons is trying to give the oxygen electron, so it's just a better base than the sodium hydroxide, things like that. It's a really strong base, and it's using such a strong base that I think it should just indicates how isonitrile is not the big, it isn't really just not that good of a leaving group, so you have to use like this strong base. Acorns in last step, the Ambiguine P. Our final journey finds its end. This is how we're going to end it. This is the Riley oxidations. Now this oxidation is tricky. You can look up the mechanism of this reactions, or the Se, the selenium, is going to act as this is a cyclic transition state, and what happens is that this oxygen will attack this hydrogen in the first place, the cyclic transition state, and move up to the next step. This oxygen will attack this double bond again, and trying to, not again because it's a different oxygen, and this double bond will bounce back and trying to knock off this selenium. And then this is a very like hypothetical transition state. Maybe there's this computational chemistry work on it. I don't exactly know about it. I think it's right. And then do some hydrolysis afterwards. You get this molecule. So the hydrolysis is just like the usual hydrolysis. This O connecting to the selenium would be trying to grab another piece of hydrogen cation, trying to leave because it's a good leaving group afterwards. A bear a formal charge on it. Easy to leave by another nucleophilic attack by a mole of water. Not mole of water. What am I saying? Another water. Just by another water. And just like this. Yeah. So just to see how is it. So yes, thank you very much. Thank you very much for listening to this video. Thank you so much for watching my first video. I'm gibberish-ing a lot, I knew it. This is probably the 17th take. I was stuck in the middle quite a lot. Yeah, so that's all. Those So these reactions pictures are from the ChemistryByDesign.com. It's a really good website by a professor in Arizona University, I guess. I kind of forget about that. I'm so sorry. Just check out that website, please. Yeah, it's a really good website. It's a bunch of synthesis routes on it, and the original paper and some reference I'll put in the description. Cool. So yeah, that's my first video. Thank you guys so much for listening. Yeah, thank you.